Okay. Matt, are you? Matt, have you got the bin going?
I do.
Oh, is it circulating?
It's right here, right now. It's circulation.
Does it get circulated? I don't know how that works.
So, all right.
Where's the money actually go?
SPS.
Blue Jays.
Yeah. For the camera, Alex.
Sure, yeah, maybe the world will say this. Yeah.
All right. I don't. What is the link?
Is it recorded?
It is. All right. So next Friday we have our Paya Prof event where if we raise enough money for Alex, money goes to SPS. We are going to pie him in the face on Friday at 1 o'clock. If we raise double, which is $50, then next Thursday during lecture, we are going to pie Alex a second time. So,
And it's after the midterm.
and it's right after the midterm.
Oh, good.
So we might all really want to pie him in the face at that point.
Will it be
Here's my Venmo code.
YouTube and watch it?
Try and scan it. I don't know.
I vote yes, but that's
I
not.
don't know where the focal length of this camera is. There you go. Good luck. Good luck.
Focus.
You good to have it on camera?
Is it autofocus?
All right. Yeah. Yes, it will be on camera. Whoever asked that. All right.
That's what the internet was on.
Okay, Matt.
Yeah. All right. I'm just gonna circulate this bin here.
That was your 15 seconds.
That was my 15 seconds.
Hey Matt, have you put any money in there?
Okay. Shh. All right, we do have to at some point do physics, so let's get started with that. Okay, so again, for those of you who weren't here last time, for your midterm next Tuesday, you should be primarily focusing on all of the homework and homework quizzes that you've looked at so far, and of course, the solutions to almost all of those are posted. I will go and post the solutions to the homework and homework quiz from last time tonight. Say it again?
Is this open? No. Do I actually have to like note things in my head?
Yeah, it's open. Okay. All right. So last time, hey, children. Last time we talked about how when we want to start doing calculations, particularly to compare with experiment, we kind of focused on two quantities that might be of interest. And Martin is off in, I think, in Mexico climbing, so Levi is going to get to remind me what are these two quantities and what are they relevant for? So what is gamma I?
Where was the scattering cross-section? That's the sigma.
So that's the sigma I, so that's the scattering cross-section. If we send particles together and they interact and then go off, sigma I is basically a measure of the probability per unit time of a particular scattering event. So Levi, you get to phone a friend for gamma I. You can pick Kowalski. He's smiling.
All right, yeah, the probability of decay, or a particular decay.
Yeah, so this is the quantity relevant for particle decays. And typically we think we have a particle sitting there and then all of a sudden there are particles coming out. And so this is the decay rate for a particular combination of outgoing particles. We can have different things come out, so that's why we have different decay rates. Now, what we're really going to focus on is calculating these two quantities, and it turns out that when we do the calculations, they're going to roughly, not entirely, but almost entirely break down into two contributions. The first is going to be from kinematics, and the kinematic part is really just going to be constraints for conserving energy and momentum, for things making sense in terms of having positive energy. And what we're going to find is that the kinematic part of the calculation can be sort of summarized in what's called Fermi's golden rule, which we'll talk about in detail in a moment. And we'll have a version of the golden rule for decays and a version of the golden rule for scattering. We're not going to derive it, but we'll try and make sense of its form. And then within Fermi's golden rule, there's going to be one quantity that is still undetermined, and that turns out to be the quantum amplitude for the process. And to calculate the quantum amplitude for the process is where we actually turn to the dynamics. That is, we actually ask, what are the interactions that are involved what are the degrees of freedom other than space-time energy and momentum that are important. So in particular, spin plays a very important role. And in calculating the amplitude or handling the dynamics, that's where we are going to find ourselves for the first time introduced to the Feynman calculus. And this is a computational method based on constructing Feynman diagrams, and then for each Feynman diagram you evaluate the corresponding quantity. And we're going to learn how to do all this today. Okay? So at the end of today, you should be able to walk out of this room able to evaluate at least a Feynman diagram for a toy model, and then we'll start looking at the details of the more complicated electrodynamic case next time. Okay, so the first thing I want to do is hand you Fermi's golden rule, and I'm going to kind of do it for both cases simultaneously so that we can make comparisons. And then after we've got Fermi's golden rule in our pocket, we're going to spend most of our time focusing on calculating the amplitude with the Feynman method. So to begin with, so Fermi's golden rule. So we're going to start with the case of decays up here. And I'm going to think of, for simplicity, a particle of mass 1 which is at rest. Okay? We could always do the calculation for a particle at rest, and then we could find what the corresponding answer would be in any other frame of reference, so we might as well do it in the simplest one. So for a particle which is sitting there happily at rest, and of course it has to have to be a particle of mass to be at rest, but if it has some mass in 1, then we're going to be considering that particle decaying into a collection of things, and it can have 2, 3, 4, whatever, up to, we'll say Mn will be the last particle that comes out. And this, again, is just going to be one particular possible decay. So this would be the ith channel. So when a given particle decays, it can decay in different channels. A channel is just a set of decay products. Okay? So maybe one channel has 2 things come out, maybe another channel has 3 things come out. We have to do the calculation one channel at a time. Okay? Yeah?
Are there products at rest, or can they have different speeds?
Well, so we can answer that question from a kinematic constraint. So what would have to happen for the particles to come out and themselves all be at rest?
Be in the same place.
Or like, if they go in different directions?
Well, are you saying if the first particle's at rest, is it possible for all of the particles that come out to also be at rest? Is that what you're asking?
Like, do they don't have to be at rest on the
Okay, so the kinematic consideration, which is part of Fermi's golden rule, but the kinematic consideration is if you take the mass of what you start with, and then you take the mass of what comes out, those 2 masses don't have to agree. Because this is relativity. You can liberate energy from being in the form of rest mass to being, say, kinetic energy associated with motion. So if the total mass you start with is different than the total mass you end with, and if it's different, the total mass at the beginning has to be larger than what you end with, then that leftover energy goes into the motion of the particles that come out. So the only way those particles could all be at rest is if their total mass was exactly the same as the total mass of what you started with. Okay, which is a very hard scenario to cook up, given the masses of the particles that we observe. Okay, but those kinds of conservation of energy momentum and mass is a part of that story because it's relativistic energy momentum. That's all built into the calculations that we're doing. They're almost not things you have to think about separately. Okay. So, all right. So the expression for the decay rate associated with a particular mode I is going to be given by a factor S, which I'll talk about in a moment, over 2 h bar times the mass of the thing that is decaying. And then the rest of this expression is the magnitude squared of a quantity we're going to call m, and m is that thing which is the quantum mechanical amplitude for this process, and that's the thing we're going to have to use Feynman's calculus to evaluate. So we're going to spend a lot of time determining what m is. And then the rest of this is really just a bunch of delta functions which enforce the things we might expect for the kinematic quantities. So we have, and I'll just go, what I'm actually going to do is write all this down, and then I'm going to go back and give everything an interpretation. And by the way, for anyone in the room who is not familiar with delta functions, you need to get familiar with them. We are going to use them a lot, but the good news is, as you hope you are aware from quantum mechanics, they are your friend. Delta functions, good. They make evaluating integrals really easy. We are, however, going to throw in a step function because, you know, why not? And then there's an integral sign, so I have to give you a measure for integration. So we'll measure over all four momenta. Okay, so now before I actually pick this thing apart to give an interpretation to each of those terms, I'm going to go ahead and write down the result for a scattering event because it takes a very similar form. Okay, so for a scattering, so let me give myself the right amount of room, where I'm going to, for simplicity, think of two particles scattering. So two particles come in, and then I can have a lot of different numbers of particles come out. But generally speaking, two particle collisions are the easiest things to cook up. It's kind of hard to get three things to collide at once. And even if you have three particles which are sort of colliding, you can almost do it in, unless there was some miraculous coincidence of the events, you could do it two particle collisions at a time and build up the three particle collision. So two particles are going to come together, and then out of that process is going to be a collection of particles. And again, it could be the same two particles you started with, but you could have those particles disappear and have different particles come out. And in particular, you can have a different number of particles come out. And of course, this is going to be the ith channel for scattering, because there are different results that you can get when you take two things and slam them together. Sometimes you get this, sometimes you get that. Each possible outcome is a channel, so this is going to be for the ith channel. And then the scattering cross-section for the ith channel is going to be given by the following factor. That's a 4. This is a root. P1.P2 squared minus okay. So now you'll notice there's a lot of common ingredients between these two expressions. And so now let's actually start looking at the common ingredients and sort of giving an interpretation of what they're doing for us. So first of all, you'll notice they both carry a factor of m. Okay? And m is going to be this quantum mechanical amplitude, which is going to take into account, Jason?
In that delta, the fourth on the second one, is it P1 plus P2 minus P3?
Yeah, that's a 3. Any, what do you call a typo that you make on the board?
Righto.
A mistake? We always got to be fancy with our language. Any mistake that I make, it'll be easy to correct after I interpret these terms. So anyway, okay, so there's this factor m, and what m is really doing is it's the following. For a decay process, what we have in mind is we have some particle 1 that exists in existence at the beginning, okay? And in all of the pictures that I'm going to draw now and later when I look at Feynman diagrams, we kind of think of time as flowing to the right. Okay? Now, I will go ahead and stress to any of you who might have other references that you look at for particle physics, there are different conventions. Some people do time flowing up, some people do time flowing to the right. In this course, we're always going to use time flowing to the right to interpret things. So we have particle 1 initially, it exists for some amount of time, and then at the end of everything, we have particles 2, particle 3, particle 4, etc., particle n. And what the m factor is doing for us is it's actually going to fill in the gap here. So the m squared is really how do you connect the thing you start with to the things you're ending with. The rest of the expression is really just talking about how this and the kinematic quantities associated with this are related to the things that are coming out. So the really interesting part of how it actually happens is going to be caught up in m. And we're going to talk about how to calculate m in just a minute. For decay, or for scattering events, we can do the same sort of dance. This time we have 2 external lines because we're having 2 particles come together. And then we have a set of particles which come out. And we might have 3, 4, up to n coming out. And then again, the business of how you actually combine or join all of these things is going to be captured by this quantity m squared. Okay? So the fact that we have to join everything for a decay and join everything for a scattering event is reflected in the presence of this m squared term in both of these. Okay, so now I'm going to pick the lucky loser, I think that's the right way to phrase it, who gets to interpret this term in each of these expressions. And for bad saying that, the lucky loser is Patrick. Right, Patrick. Patrick, what do you think that term, delta function P1 minus P2 minus...
He's not here.
Oh, he's not here. Well, then you're going to answer it for him. What do you think this delta function is doing for us? Are you comfortable with delta functions?
Not really.
Who's comfortable with delta functions?
Oh man, who's gonna raise a hand now?
Oh man, I got Spencer and Matt. I got the boys in blue.
Oh, come on.
Who's going to do it? Who's going to throw down? Matt's already had his 15 seconds of fame. Spencer, come on up front and tell us about delta functions.
Really?
No, I'm kidding. What do we know? What do we know about delta functions inside of integrals?
Delta functions really sift things, right? If you have a delta function inside of an integral, it tells you what you're looking at from the rest of the function.
Okay, so if I have a delta function, if I'm integrating over x and I have a delta function whose argument is x, then what does that do to that integral?
It turns the function, it gets rid of it.
Matt,
Makes it 0 everywhere else.
except for?
0.
Yeah, so the delta function gives you a contribution to the integral that is 0 everywhere except for when the delta function's argument vanishes, okay? So the real use of a delta function is when it sits inside of an integral with another function, because what happens is this thing is essentially 0 for x not 0, and it's kind of like 1 for x equals 1, which means if you're summing over all x's, which is what an integral is, then this just returns f of 0.
Yeah.
Okay? Now, of course, you can cook the argument up and you can say, okay, delta x minus 1. And in that case, what would it return? F of 1. Because it's always going to return the value of x that makes the argument of the delta function 0. So this is 0 when x is equal to 1. Okay? So with...
So does that imply that m is in terms of p? Like the m squared?
Yeah, so, well, right now we're going to talk about what m is, but in general, yeah, m is typically going to depend on p, but it might not. We'll see examples where it doesn't. Okay, so we'll get to that point eventually. Okay, so now looking at this thing, what is this delta function doing for us?
I don't know, what's it on?
It's a delta function. Well, first of all, it's a four-dimensional delta function because we're in 4 dimensions, and it's a delta function on 4 vectors. I should say, I should stipulate this. In all of these expressions, all of the p's are 4 momenta. So there are 4 vectors. We're just going to leave off the indices because everything is contracted. So like p1 dot p2, this is p mu, and so forth and so on. It's just these are already cumbersome expressions, so we're not going to try and put indices in here. Yes?
Is that term not just saying conservation of momentum?
Exactly! Perfect. Yeah, I yelled because it's important. This is conservation of overall 4 momentum. Okay? All it says is I want the 4 momentum going in to be equal to all of both 4 momentum going out. Okay? This argument is 0 when P1 is equal to P2 plus P3 plus up to Pn, and in this case it's 0 when P1 plus P2 is equal to P3 plus P4 plus up to Pn. Okay? Again, here you just have 1 momentum coming in, and this has to be equal to all the momentum coming out. Here you have 2 momentum coming in, and that has to be the same. The sum of that is the same as the sum of all the momentum coming out. That's all that delta function is doing. Okay? Okay, so who... Find somebody who's actually here. Everybody's skipping class today. Madeline. What do you think this delta function is doing? Conservation of energy is actually part of this story because 4 momentum includes energy and spatial momentum. So it's a good guess. I mean, you certainly got things in here like this kind of looks like rest mass energy. You've got some momentum stuff going on there. But the actual conservation of energy is the time-like part of this expression. So that's enforced by this delta function. So what might this guy be enforcing? Conservation of mass. Well, actually, maybe, well, yeah, maybe where this is getting confusing is because this is a place where our change of convention that we talked about last time is actually reflected. Okay, so first of all, this is a product from j equals 2 to n. So this j is labeling these things. It's not labeling this. Okay? So it's just labeling the things that are coming out. And over here, the j goes from 3 to n. So again, it's just labeling the things that are coming out. Okay? And then if I just look at one of them, say j equals 2, what this is saying is that it wants the momentum from particle 2 to square, you square it, and you want that to be equal to the mass of particle 2 squared times c squared. Okay?
Was this a Mathshell condition?
Yeah, so this is a condition that we discovered in special relativity called the Mathshell condition. And it just says that if I take the 4 momentum of something and I square it, I can evaluate that in any frame because it's a square. It's an invariant. In particular, if I evaluate it in the rest frame, the 4 momentum of a particle just looks like this. Okay? Now, actually, that's the 4 momentum here. Now, the important difference now with our convention is that when we dualize the momentum, before we would have put a minus sign in front of the time-like component, and then that would have been minus mc. But with the new convention, the minus goes in front of the space-like component. So in that case, it doesn't change the sign. You just get mc times mc, so you get m squared c squared. Okay. So to put this, to make this a little more, to maybe remind you what this looks like in an arbitrary frame is E over C, and then this is the relativistic spatial momentum. And so when I dualize it, I get E over C minus P, and then when I do P mu, I get E squared over C squared minus P dot P. But again, this is an invariant, so it has to be the same as the value we would have gotten in the rest frame. And so this is a condition that we called the Mathshell relation. And it's just a relationship between the relativistic energy of something, the relativistic spatial momentum, and the mass. So for any real particle that we observe, this has to be satisfied. Jacob.
Why is that something we need to impose on it? Like, is it not just something that's built into our construction of how we connect dual vectors with?
Well, no. So, what? It's built in to this calculation because we're imposing it. So so one of the things that you want to do is you want to look at all possible outcomes. So once I give you the masses of these, once I say what these things are, then you know their masses. But then, if you've got some energy and momentum to distribute, you can change how much you give this, how much you give this, and how much you give this. But you have to be careful, because if you give this so much energy, you've also got to give it so much momentum. You can't just arbitrarily assign the energy and the momentum separately. They have to be tied together through this relation. And that's what this does for us. Okay, so these expressions know about special relativity because these factors are there. If these factors weren't there, then it might be that you would allow for particle form to have, some amount of energy and some amount of momentum that might not satisfy this. Okay, and the reason I say that is because we're going to integrate over those four momenta. So these four momenta, when we integrate for each of these particles, this is an integral over the zeroth component, which is the energy, and an integral over the spatial momentum. But when you have an integral over those things, in principle, the integral doesn't know. It lets all values of both of those things, you sum over all possible values. This is constraining you. If you're going to set the value of E to something, then the value of P has to be the corresponding value to fix that. So that's what that delta function is doing for us. It's limiting the combinations of the components of this P. Okay? So, and of course this factor happens in both of them. And really all it's doing is saying, I want the particles that come out to be real particles. Like I want them to satisfy the relativistic Mathshell constraint. We don't have to worry about that for the particles going in, because those are quantities that we fix. We set what's going in. So we say, I'm going to take this and slam them together. The question is, what are all the possible outcomes? And in enumerating those possible outcomes, we have to make sure to satisfy these conditions. Nathan?
Well, so does this rule not hold in QFT, or are offshore processes not actually observed?
No, we're going to get to that. We're going to get to that. It holds, so this is going to be the result from QFT.
Yeah.
But the important observation is that these conditions have to hold for anything that's observable. That is, anything that starts off to the left and ends off to the right. But anything that happens in here, all bets are off, because you don't observe this. Okay? All right. Does anybody want to take a crack at the step function? Who's having a particularly good day? Go for it.
Those particles don't exist until the decay. After the decay, because your step function turns on at 0, whatever your argument is. So
what is the argument of that step function?
0 and j. I think that's a 0.
So it's the zeroth component of the jth four momentum. So for one of these four momentum, it's saying that the zeroth component has to be
positive.
Positive. The step function, so remember a step function, so theta of x is 0 until you hit the value of the argument, and then it jumps to 1. Okay? So this is just enforcing that the particles that come out have positive energy. Yeah, they just have to have positive 0th component of the form momentum. Again, that seems like something like, of course, but think about it. You could potentially put in negative values for the energy and satisfy this Mathshell condition. So just satisfying Mathshell doesn't alone make the energies positive. So this adds the extra step of saying these things have to have positive energy. Okay, which, you know, if you think about it, of course they do, because they have positive mass, so the rest mass energy is positive, and then any additional energy is just kinetic energy, which is always positive. But again, this integral is stupid. It doesn't know what P is. It's just going to sum everything up from minus infinity to infinity. Now, that's okay for the spatial momentum components. For the spatial momentum components, the spatial parts of the form momentum, you can have positive and negative values. Momentum can be positive and negative. But the energy can only be positive. And again, this is not potential energy, binding energy. These are kinetic energies, essentially, so they have to be positive. Spencer?
So I know we haven't talked about Feynman calculus yet, but theoretically you should be able to do this in reverse, right? So like associate a negative energy with like the reverse process in a Feynman diagram, or associate negative time and it should still hold or something. You know what I'm talking about?
Anyway, so if we then, yeah, I know what you're talking about, and we're gonna, so when we do the Feynman diagrams and we're focusing on what's in here, that is where we're going to, so when we start doing the Feynman calculations, okay, we're going to find that we have to assign momentum flow. And one of the observations is going to be that for any physical particle, the momentum flow always has to be in the positive direction, the momentum flow. Okay? But for the interior particles, we can actually choose it to be any direction we want. Because again, we don't observe those, they're virtual. And so you can give them this funny interpretation if you like. Okay? Now, that's not to say that we won't have antimatter as possible things coming out of a process or things going into a process. But even when we have antimatter, we're going to have a positive momentum flow. The way that we're going to recognize that it's antimatter is we're going to have a negative flow along the particle's identity. And that's something that we won't even see until we get to QED. It won't be part of today's story, but we're going to get to that in time, I promise. And I would never ignore your question, I was just playing. Okay, and then lastly, these things are tied to the integral signs, because after all, there was an integral at the beginning of all of these expressions, and if you're going to integrate, you have to have an integration measure. And so, really and truthfully, all that the integral with these momentum are saying is to add up all possible configurations of the outgoing momenta. Okay? So again, the likelihood of a process, which is what this is calculating, this is the decay rate, it's the likelihood of this process happening, this particular decay channel happening. This is the scattering cross-section, it's the likelihood of this particular process happening. And the likelihood is in part determined by how many possible final configurations there are. The more final configurations that are compatible, that's another way of saying that is the larger phase space is for the outgoing part of the process, the larger the probability. But that's exactly what we see because we're integrating over all possible combinations of outgoing energy and momentum that are consistent with these conservation principles and reality constraints. So the more of those combinations there are, the more likely the process is. And again, the example that I ended with last time, just to give this a physical interpretation, is if I have M1 and it decays into M2 plus M3, or it can decay into M4 plus M5, but we find that M1 plus M2, or sorry, M2 plus M3 is 0.999 M1, whereas on the other hand, M4 plus M5 is 0.001 M1, then what these particular two situations are describing is this particle can decay into these two things, but there's very little energy liberated from rest mass energy. Okay? Because most of the energy that you start with is still caught up in the rest mass of these. Whereas in this process, almost all of the rest mass energy is liberated because the total rest mass energy you end with is just a tiny fraction. So what that means is that you've got this huge bucket of kinetic energy, which you can also think of as momentum, to distribute in this case, but not nearly as much to distribute in this case. And so generically, we would expect this to be a much more probable occurrence than this one, because the phase space, the different contributions to the integral over all the configurations of the final outgoing energy and momentum, you've just got more possibilities here than you have here. Okay? So that's just one particular reflection of it, but it's all built into these two expressions.
Do these expressions reflect that you can only have massive products? You can't generate photons or anything like that from scattering or decays?
Oh, no, yeah, no, why do you think that you can't have a mass?
I guess a better question then is, does a photon still satisfy the Mathshell condition?
Sure.
What do you plug in for M?
Zero.
Just the theoretical mass?
Zero.
It still works?
Yeah.
Okay.
In fact, if you write down the form momentum of a photon or anything that's so the form momentum of a massless particle is just E over C, and then just pick one of the momentum components. It doesn't matter which one. One of the components is going to be minus E over C. Oh, sorry. It's going to be plus. And then when you form the dual, this will pick up a minus, and then when you combine them, they'll be zero. Yeah. Rochelle.
So you were saying that the bottom one is more likely because we're adding that more in the integral, like we're adding more of the different formations together?
Here, well, I want to be a little bit careful because the two-body process is particularly constrained. The particles have to come out back to back. This might actually be so constrained that you really couldn't see it. But if you imagine like there were 5 particles here,
Yeah.
and then you could pick how much energy to give each of them, then you have a lot more possibilities. For these particular examples might not have been the best choice just because they're constrained to be back to back with the same momentum magnitudes and then therefore the same energies. Well, no, they could have different energies depending on their masses, but.
I guess what I was wondering is if you're adding together all of them, and that's giving you the number of possibilities, then why do we even need the M? What does the M even do if the likelihoods determined by the different configurations that we're adding up to the integral?
This?
Yeah.
Oh, you're going to find out. You're going to find out. The M is, so right now it seems like, this is all that matters is these constraints, and if you satisfy them. But it's going to turn out that depending on how you connect the lines, that can dramatically change the likelihood of the process. So, but that's what we're going to see when we actually start building the Feynman diagrams and evaluating them in just a few minutes. Okay. All right. So there's one more thing in here to go over, and that is these. So the coefficient factors are not that important at some level. This is obviously some statement about what's happening with the initial momentum and mass, and here the initial mass. But this factor S, I just want to touch on that. So S is going to be a product of inverse factorials. Where SI equals the number of identical particles of type I. Okay, and the reason for that is mainly we have to be careful because say our decay channel included an electron here and an electron here. Okay? Well, I want to be careful because if I say that this electron comes out with so much energy and so much momentum, and I say this say this is an electron and it comes out with energy E1 and momentum P2, or P1. Sorry, P2 and E2. And this is an electron as well, and it comes out with energy E3 and P3. Okay? In doing the integral, I might later assign this electron the same numerical values of energy and momentum that I had assigned this one, and vice versa. But those aren't distinct outcomes, because you can't tell these electrons apart. Electrons are identical particles. So all you really care about is that one electron comes out with this combination of energy and momentum, and a different electron comes out with a combination E3, P3. And I don't actually care which of the electrons I assign it to, because electrons are identical. So this combinatorial factor is just accounting for that degeneracy. Okay? Identical particles are truly indistinguishable. The only way I can distinguish them is their energy and momentum. Okay? All right. So really and truthfully, the quantitative statement of the golden rule is that all possible outcomes in terms of, if I've already said 2, 3, 4, up to n, so for a given channel, if I've specified what the particles' identities are, all the golden rule says is that all possible outcomes, that's all possible configurations of energy and momentum, they're equally likely. So the probability is just the sum of how many of those possibilities there are, and that's what the integral is giving us. Okay? So the more possible ways of distributing things, the more likely that particular process. Okay, so I really feel like it's important for us to do some Feynman diagrams today. I'm going to flash 2 results up to you, which are particularly useful results, but I'm not going to spend a lot of time developing them. But they follow from the golden rule, and they are actually hugely applicable results, so they're really worth at least writing down. So generally speaking, when we evaluate the m's, okay, well, you might ask yourself, can you do these integrals? Because you've got a whole bunch of delta functions. Maybe you've got enough delta functions to be able to actually completely do the integral. Okay? Well, the problem is that when we calculate m in a minute, we're going to discover that m itself is going to contain integrals. And we're not guaranteed that at the end of the day, the full expression is going to have enough delta functions to take care of all the integrals. Okay? However, there are 2 special situations where even before you calculate m, you already know that you've got enough delta functions to completely evaluate the integrals. Okay? And those 2 special situations are, and I'll just write down the results for them. So for 2-body decays, where a 2-body decay is really just one particle decays into 2 particles. Okay? So the 2-body here means 2 bodies come out. For 2-body decays so I'm going to label these 1, 2, and 3 with M1 at rest. Okay, as usual, we have the following expression for this channel. It's just S times P over 8 pi h bar m1 squared c times m squared, where so notice no integral. The momentum p here is the momentum of either of the outgoing particles. It doesn't matter which one, because if you have 2 particles coming out from something that's at rest, they go out back to back with equal and opposite momenta. Okay? And then the actual value of that outgoing momentum, and this is a calculation just using relativistic kinematics, is given by this expression. Which is probably what you would have expected if I had just asked you, hey, what do you think that expression is going to be? You'd have probably said, it's going to be either 42 or the square root of a whole bunch of stuff. Okay? Okay, so if you're looking at a particular case of two-body decays, there's no point in looking at this expression. You can just skip straight to this guy. You're still going to have to calculate m, but after you calculate m, you just multiply it by this factor and you're done. In any other decay, you have to calculate m, put it in the integral, and then evaluate the integral. Okay? And then for the scattering case, we can consider two-body scattering. And for two-body scattering, of course, we have two things come in, two things come out. But we want to make sure this is as simple as possible, so we're going to consider two-body scattering in the center of momentum frame. Okay? That is essentially saying that the two particles that are colliding are coming in head-to-head with zero total momentum. And then you know why this is now similar to the two-body decay, because then the two particles that come out have to go back-to-back with zero total momentum. So that's why this is going to simplify in these two cases, because the particles coming out are so highly constrained. They have to have the same magnitude of momentum, and they have to be moving in opposite directions. There's not a lot of freedom in how you can distribute things. And so in this case, the scattering cross-section is just going to reduce to h bar c over 8 pi squared s m squared over E1 plus E2 quantity squared times the ratio of the final momentum of either of the outgoing particles magnitude to the magnitude of either of the incoming particles. Again, it doesn't matter which of the outgoing particles you put here, because they move back to back with equal and opposite momentum. So they're going to have the same momentum magnitude, and the same with the incoming, because you're in the center of mass frame. Okay? So again, if I tell you it says two-body scattering in the center of momentum frame, then don't bother with this expression. Just come down here and say, okay, I calculate m squared, and then I just plug it into this algebraic expression. Okay. Questions about this? Are you guys ready to find the calculus? Let's do it. All right. So now we're going to spend the rest of today and quite a few of the next few lectures focusing mainly on that quantity m, how to calculate m. And we're going to start, and when you do like sort of, whenever you start doing like new, very abstract physics sort of context, it's always useful to try and start with a really, really simplified version. So we're going to work in terms of what's called the ABC toy model. And the beautiful thing about the ABC toy model is that it has no information whatsoever about spin, because we know spin sucks. Okay? So we're going to do a toy model. Called the ABC theory. And the ABC theory is going to be based on the following Lagrangian. Actually, sorry, phi A. And bear in mind, I'm writing down a Lagrangian, so this is where we will have some of those changes in convention that we talked about last time arising, in particular in the Klein-Gordon Lagrangian term. We're going to have a minus in front of the mass instead of a positive sign. Okay, so far, completely boring theory. Why? Wolfgang, why is it boring?
Because
Matt, the show-off Kowalski, has the answer.
They don't interact.
They don't interact, exactly. These are three particles that are just freely propagating. They don't touch each other. They don't interact. Okay? That's boring. We could calculate processes, amplitudes all day long with that. Okay, but we want it to be interesting. So we want interaction. So we're just going to throw in the most perhaps simple interaction we can imagine. It's just going to be
Oh, that was good.
it's going to be a product of all three of the fields. Okay? Now, let's just take a moment before we dig into the rules to talk about what this theory is describing. First of all, given the form of the kinetic terms, what kinds of particle or what kind of fields are these? They're scalar, they're spin zero fields. So these are three spin zero fields. Okay? They're real because there's nothing in here which is indicating that anything's imaginary. There's no complex conjugation. Okay, the Lagrangian has to be real, so that means that these phis themselves are real. And what we'll discover later on, or you might remember that we discovered from the Dirac equation, was that the presence of antiparticles was tied to the fact that the Dirac spinors were complex. Okay? Now it's not necessarily obvious that a complex field is a field which will give rise to an antiparticle that's distinguishable from the original particle, but that's a general rule. In this case, since the phis are real, that means that the particles are equal to their antiparticles. Okay, so in a notation that we will adopt later on, we would say that the antiparticle for A, for example, is the same as the particle A. All right? Now, this is actually obviously not going to be true when we apply this to the real standard model because electrons and anti-electrons are distinguishable. The way that that's going to be reflected in the Feynman calculus is when I draw a particle trajectory for, say, the propagation of particle A, I can just draw a line. Okay? Later, when we talk about electrons and anti-electrons, when I draw a propagating particle, I'm going to have to indicate whether it's an electron or an anti-electron. And the way that I indicate that is by putting an arrow on the line itself. And whether that arrow points forward in time or backwards in time is telling me whether I'm dealing with an electron or an anti-electron. Again, this is not going to be important for today because everything is a spin zero particle. The particle and the antiparticle are the same, so we don't even have to indicate that flow. But that's a place where it's going to get more complicated when we apply this to QED. Now, I'm going to add in a stipulation because right now, if I don't say anything about the masses of these particles, then we don't really know what can and can't happen. So one thing that I'm going to go ahead and stipulate is that the mass of A is larger than the combined mass of B and C. And that's just something that's going to give us something to sink our teeth into in terms of kinematic constraints. So for example, MA could decay into MB plus C, but MB could not decay into MA plus MC. Okay? This is just an additional piece of information I'm giving you. You don't deduce it from this thing.
Yeah.
Okay, and then lastly, and this is the most important thing, and we're going to learn how to more systematically get this in the future. Looking at our interaction, which is the product of all three fields, we can deduce what is called the fundamental interaction vertex. It's a piece of a Feynman diagram which is encoding the interaction. So the kinetic terms are just going to be associated with the fact that particles can propagate. That is, you can just draw lines. This particle is happily moving through space. But the interaction term is where the lines meet. They interact. And so our fundamental interaction vertex in this theory is something that looks like this. It's where an A meets a B and a C simultaneously. And the fact that this is our vertex is just reflected by the fact that this is a product of all three different fields. Okay? Yeah, Matt?
Does the exact orientation of that vertex come from the mass of the A is greater than B?
No, so this is a very important observation which I'm coming to next. This vertex, when I draw it, can be rotated. Okay? Of course, the interpretation of it is different as you rotate it, but this product of three fields is just saying I have three lines that meet and they have the labels A, B, and C. It doesn't necessarily mean that they are oriented in a particular way. Okay? Now, what you can't include is something that looks like this. You could, if there was a factor minus G prime phi A phi B squared, but that's not part of our Lagrangian. We only include interactions that are in our Lagrangian. So our theory at present only contains this one fundamental vertex. Yeah?
Is there anything in the Lagrangian that's restricting us to having more than one B or C coming out? Like MA decays into two B's and a C?
Well, so this is where it gets cool, okay? So now the question is, for a given starting point, what can come out? So if I start with an A, and I ask you what are the possible combinations of things that can come out, well, I think it's pretty obvious that we can get out a B and a C. Because now, this is the fun part about Feynman calculus. It's literally like third grade, like Tinker Toys, like connect the dots. Can I connect those lines using nothing but vertices like this? Yes. Can you do it? Yes. I hope. Okay, if we can't get through this step, then we're in for some trouble. Yeah, that is literally just the fundamental vertex. Okay? Now, don't get me wrong. There are more than one ways to do this. I could, for example, take A, B, C, and instead do this, where this is a C, this is a B, and this is an A. Everybody look at all three vertices in there and notice they are all ABC vertices. Gets better than that. I can also connect them in the following way. Or I could do it like this. Whoops. Or I could do it like this. Okay, the first time you see this, you're just like, oh shit, I didn't even think about that. It's fine. The first time you work with these diagrams, it's not intuitive. And the truth is, when does this process stop? Never. Never. You can always write a more complicated diagram. I mean, here you've already seen, anytime you have a B line, you can insert an AC bubble. Yeah. So then I could insert another AC bubble. Insert bubbles. So I can make arbitrarily complicated diagrams. All of these diagrams are part of the M amplitude for this thing coming in and these two things, or sorry, for A coming in and B and C coming out. All of these contribute. Fortunately, you might notice something. This diagram has a single vertex. This diagram has three vertices. This diagram has three vertices. This diagram has three. This diagram has three. In fact, these are the simplest diagrams you can draw with three vertices. So we have a one vertex diagram and then four three vertex diagrams. And then you can actually prove to yourself that the next simplest diagram has 5 vertices. You can't draw a 4 vertex diagram. Okay? So what we're discovering is the more complicated the graphs get, the larger the number of vertices. But what we're going to find when we actually write down the Feynman rules is that for every vertex, you've got to put in a factor of the coupling G. So that means that this diagram is going to have a factor of G, where all of these are going to have a factor of G cubed. And then G to the 5th, and then G to the 7th. And the good news is that as long as G is less than 1, then we're going to find that the more complicated diagrams tend to contribute less and less to the amplitude. And so in many cases, we can get away with calculating the lowest order set of diagrams, and that effectively gives us the right answer. So this is a Taylor expansion, in a sense, in the interaction strength, where the organization of terms in your expansion is by how complicated the diagrams are. Okay? Now, this is a particular example that I'm going to go through in detail, but just to give these a name, not all diagrams have specific names, but these types do. So this thing, if you think about it, this diagram, it's almost like I took this vertex and kind of blew it up into a triangle. Okay? So this kind of diagram we typically call a vertex correction. So it is a higher order diagram which is kind of taking the basic vertex and it's making it a little more complicated. Okay? These diagrams are all corrections to the propagation of one of the particles. Here it's a sort of higher order correction to A's propagation. Here it's a higher order correction to B. Here it's C. These are called self-energy corrections. Okay, Jacob.
Is the coupling a non-dimensional quantity? Because it seems like if we chose certain units or things. Okay.
Yeah, it'll be a non-dimensional quantity. Okay. All right, so all I've done at this point is I've kind of given you an idea of how to draw the pictures. That's the fun part of the Feynman calculus. Now for the painful part. It's actually not that painful, but it's where these diagrams actually get their utility. You know, you don't draw a picture and go, oh, I calculated the amplitude for a scattering of an electron, anti-electron into a blah, 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 blah. No, you have to calculate a number. These are not numbers. These are pictures. Okay? So somehow these pictures have to get turned into numbers. And the truth is that everything that I've been sharing with you, these pictures, these... you know, the golden rule, what I'm about to share with you, all of this is more rigorously derived in a quantum field theory context. We're not going to do that. I'm just going to give you the rules. But fortunately, the rules are easy to follow, even if you don't understand the underlying picture of where they came from. So here we go. So our rules are the following. Rule number 1. Label all momenta. So these pictures, I've just got like A, B, and C. But in truth, we really need to talk about the kinematic quantities of these particles as they propagate. So for exterior particles, we'll call their momenta P. And we're going to give the interior, or the virtual particles, these are the ones that are inside the diagram, but they don't correspond to the external legs. We're going to give them a different name to remind ourselves that they're different. Okay, these are going to be called QI. And we label them with arrows next to the particle line. And I'm going to do an example of this, so most of this will make more sense when I work through a single concrete example. So what I have in mind is that's a particle line, and then I might say its momentum is like that. I don't want to put the momentum on the line itself because later when we do QED, this arrow is going to mean something different. So I have to be careful now. Okay? The PI must move forward in time. But the QI can do whatever. So the QI lines, the QI momentum, you can actually have them going backwards in time. You can actually have them going straight up, like at an instant of time. Okay? It doesn't matter. We don't have to give that an interpretation because it's not something that we see. All right? And moreover, it turns out that the internal momentum are always going to be integrated over anyway. So kind of trying to force them to go in a certain direction is kind of meaningless because we're going to integrate over them all. For each vertex, write a factor of minus IG. Okay, where G is this coupling constant in the interaction term in the Lagrangian. And what I mean by vertex is anytime you have one of these in your diagram, you're going to write down a factor of minus IG. For each internal propagator, or for each internal line, so these are internal lines. So if I have a process, like let me just draw a diagram to reference. Okay, these three lines are the external lines, these three lines are the internal lines. Internal lines begin and end within the diagram itself. Okay? For each internal line, write a factor of I over qj squared minus mj squared c squared. Okay? Where this is the square of the form momentum, and this is the mass of the particle for that internal line. Notice, if this were a real particle, what would that denominator be? What would the denominator, what would the momentum squared minus m squared c squared be for a real particle?
0.
It'd be 0. So this would be a horrible thing to write down if these were real particles. But these are not real particles, they're virtual. They're internal. They do not have to satisfy that this is 0. Okay? For each vertex, conserve form momentum with a factor of 2 pi to the 4th delta 4 of p total n minus p total out. Okay, we're just going to write down a 4-dimensional delta function. The 2 pi to the 4 just goes along to get everything right. For each vertex, we're just going to add up all the momentum that go in and then all the momentum that come out, and we're going to set their difference to 0 using a delta function. So these delta functions are enforcing energy momentum conservation just like they did in the golden rule. The difference is that some of these momentum are going to include the internal momentum. Because in a diagram like this, we will have external momentum coming in, but these will be internal momentum going out. Okay? So these are going to be delta functions in addition to what we have in the golden rule. Step 5, integrate over all internal momenta with a factor of 1 over 2 pi to the 4th d for qj. And then the last step is, after all this, you will have an overall delta function of the form of 2 pi delta, or 2 pi to the fourth, delta to the fourth, the sum of the total external momentum coming into the picture, that's whatever's coming in from the far left, minus the total momentum going out of the picture, okay? So after you've put all this together, you're going to discover a factor like this, even if you don't start by writing it down. We'll see this in an example. And then what you do is you erase it, then multiply the whole thing by I to get M. Okay? You erase this because remember, it's going to come back when you put M into the Fermi golden rule, because there's a delta function just like this in Fermi's golden rule. Okay? You wouldn't want to keep this because remember, we're going to take M and we're going to square it. And the square of a delta function is not well defined. Okay? We don't even need it though because we're already going to have that delta function in the result that we're plugging this M into. Okay, so I'm going to work out the lowest order diagram for you, and then next time, because this takes 2 seconds, and then I guess we're going to get our fun with ABC diagrams in, and that'll actually probably be a good lecture for it, because I think you guys are all going to want to unwind after, or just before spring break. So let me just do one calculation for you to kind of show you how easy this can be, and then next time we'll look at some more complicated examples. So if I literally wanted to consider calculating the amplitude for the process of an A particle coming in and a B particle coming out and a C particle coming out. Okay, so I want to calculate M for this thing. I start by constructing the lowest order diagram. Caroline, what's the lowest order diagram?
The vertex.
Yeah, you just literally fill this in with the vertex factor. Okay? So I draw the diagram, and now for my diagram I go through these steps. So I label the external momenta, so this will be PA, PB, PC. I have to make all of those momentum vectors flow to the right, because that's the direction of increasing time. So now I start writing things down. For each vertex factor, I write down a factor of minus IG. For each internal line, ooh, this is easy. There are no internal lines. I get to skip step 3. For each vertex, conserve the form momentum with a factor that looks like that. So I can say 2 pi to the fourth delta function on PA minus PB minus PC. Okay, because I have momentum PA coming into the vertex, and then I have a total momentum PB plus PC coming out of the vertex. Oh, snap! Integrate overall internal momentum. You gotta do it. Skip step 5, go straight to step 6. After all of this, you will have an overall factor of 2 pi to the fourth delta 4 P external in minus P external out. Look at that, there it is. Erase that, multiply by I, and the result is M. Okay? Now, right now, you might be like, wow, that's really for real? But if you think about it, there's nothing interesting happening in this diagram. It's literally just a single interaction, and the strength of it is G. The only thing that's controlling the likelihood of this is how strong the coupling is. When we look at more complicated, well, no, we'll wait. Do you want to see a more complicated case? No, you'll wait. Okay. We'll wait till next Thursday. But when we start having more complicated internal diagrams, what we're going to find is that their probability is going to be a more complicated result, because when I include all of these internal lines, I've got different distributions of how to give the internal momentum to different things in the picture. Okay? So generally speaking, the final result for M is going to be nowhere near this easy. because there's a lot more interesting dynamical things happening within the diagram. Okay? Jacob.
So is the mass actually bigger than that since we didn't account for other possibilities happening?
M is the amplitude. Is that what you mean?
Oh.
But
it's
okay, yeah. So maybe what I should do is I should call this M1.
Okay.
And then I would calculate M3, which would have 4 contributions, those 4 diagrams I drew, the vertex factor correction and the 3 self-energy corrections. And then I would go and calculate M5, which is going to have a lot of contributions, M7, and so on and so forth. And then M is just M1 plus M2 plus M3, etc. Okay? And then in Fermi's golden rule, I want to do this. But of course, what we discover is that the higher order contributions to M for a theory with at least a small coupling G, the higher order diagrams are going to count less and less. And there's other ways that the higher order diagrams can count less and less, and we'll cover those as we go through examples.
So when you, like, let's say we're just using the case of M1, if we put that back into the golden rule, how does that interact with the delta function?
So that's the thing. For this, if you just took this as your final answer for M and stuck it into the golden rule, then the golden rule almost trivializes, right? Because, I mean, well, no. Okay, so sorry, I don't have the golden rule up here. I wish I did. But you could literally take, so let me go back to my piece. Here we go, with the golden rule. I have the golden rule somewhere. Oh, there, no. What's my golden rule? Oh, here it is. Yeah. So with the golden rule, I'm not going to write the golden rule down again. You find, among other things, that you have the integral of M squared. So now I would literally just put in G squared, which I could pull out of the integral. Like, that's easy. In other cases, the M expression will end up being functions of momenta. And then you've got to leave it in the integral because you're going to do an integration over momenta. But at any rate, what I find is that I have one delta function, which, again, it's the one that enforces total energy momentum conservation. So P total in minus P total out. So this is part of the golden rule. That's why I erased it from M. And then I get delta functions which make the particles, the internal particles, the external particles satisfy the Mathshell condition, sorry. And I integrate over all of the the external momentum. And the thing is you've really only got one delta function that you can use to evaluate the momenta. This is just constraining components of momentum to agree with each other, but it's not saying the momentum has to be this. It's just saying if the energy is this, then the momentum has to be this. So you've got one delta function that you can use to relate incoming momentum to outgoing momenta. So depending on how many of these external momenta integrals you're doing, like if you only have 2 external momenta, then you can use this delta function to completely evaluate the integral. If you have more than 2 external momenta, then this delta function is not going to be enough, and you're going to actually have a leftover momentum integral to do. And so that's why when I looked at 2-body scattering and 2-body decays, in that case you only have 2 external momenta coming out, and so you could completely evaluate it using that one delta function. I don't feel like I answered your question.
Yeah, so what I was trying to say is, G.
I just said a whole lot, and you're just like looking more and more disappointed. Like, no, Alex, that's not enough.
G isn't. It's a constant, right? It doesn't
G is literally the coefficient in that Lagrangian term. It's a constant.
Yeah. So I just don't understand because I thought that a delta function has to act on a function that is of the same derivative.
Well, I mean, you. Well, no, yeah. I mean, G is not the only function that's going to be sitting inside of this expression for Fermi's golden rule. You have a whole bunch of other terms in there that this delta function can be combined with to evaluate. No, you're not buying it. Well, no. Oh, wait a minute. Okay, so there's the integral of a delta function with no other function in there. Okay, what's that equal to? It's equal to 1. Because secretly what you could do is you could put a function in here which is the function 1. And the function 1 when x is equal to 0 is 1. And so evaluating just using the normal delta function convention just gives you back 1. So this is a way to interpret what an integral of a delta function by itself gives you. So if you crammed in, all of the stuff here and you ended up with just a single integral over a delta function, then that's just going to be similar to evaluating an expression like this.
Okay. I was just thinking because there's like multiple different p's in that expression.
Yeah, and that's the thing. You really have to be careful and like break this up into integrals over the temporal part of the momentum and then the spatial parts of the momentum, and then you can actually take 4-dimensional delta functions and break them up into a product of delta functions over each component of the momentum. And then you can use the delta functions a component at a time. We haven't gone into the details on that, and we really won't do it very much in this class, but that's the way you would actually work with these 4-dimensional delta functions. I don't know if did you work with higher dimensional delta functions in your other classes?
In E and M.
In E and M. Okay, in E and M is a place where you might encounter this eventually. But, yeah. Rochelle, will you turn the camera on?
No, I saw it.
There's a button on the other side of the camera.